So what do we recognize, first of all, obviously, is that the value goes up, and that's logical. Why is it logical that the value goes up? Based on last class. Yeah? The weight increases. Very good. So as we add additional coffee filters, the assumption is that it's double, triple, quadruple, quintuple the mass each time. And it is. Right, 2 coffee filters is twice as massive as 1 coffee filter. So in each of these successive runs or trials, what we're doing really is we're increasing the amount of weight pulling down on the object. What combats the weight pulling down to cause it to reach terminal velocity? The drag. So in this problem, really, like somebody tell you you're such a drag. Oh, you're such a drag on things, man. Downer. So being a drag, the drag force retards the motion. It slows down the motion physically. Okay, it impedes the motion of this object. So instead of accelerating down further, the drag force balances the weight. Now, if you read the lab carefully, and I don't know how carefully you actually read it because we kind of ran the procedure together and you might have started collecting data right away. But if you read it a little bit further, you'll see that the assumption here is that the moment the air filter is dropped, it reaches terminal velocity. That's the assumption in this lab. Maybe jot that idea down if it didn't come to you last time, if you didn't come across when you were reading. The instant the coffee filter is dropped, it reaches terminal velocity. So, what do we know though? We know that in this case, the terminal velocity it reaches is going to be a certain value depending upon the number of coffee filters. And let's discuss that, right? So yeah.
I'm kind of like a theoretical sort of question.
Sure, good.
Is there say you have like a dime and a coffee filter or like a few coffee filters, they're about the same weight. Is the reason the dime has less drag because of its area?
That's one of the reasons for sure. Yeah, absolutely. The very, very, very small area of the cross section of a dime or a nickel or something like that versus the coffee filter, yeah. Area, and that was one of the variables in the formula. So that's what we're about to do actually. So if we think about the formula here that we're going to be looking at, we're saying that the drag force acting up minus the weight acting down eventually reaches terminal velocity, meaning the acceleration becomes 0. So this term drops off. And as we stated last class, drag force is a function of several things, one of which, as Tristan mentioned, is the area. Now, what I want you guys to figure out, or what I want you guys to think about is this. I don't want you to go into all the parameters, and that's not what this lab is about. It's not about getting into like density of the air, the cross-sectional area, the C value, right, that drag coefficient. What we're going to really focus on is the relationship that exists. So first, we can say that, okay, drag force equals weight, right? Move the weight over to the right side, like we said last time. And then drag force, we said, could be 2 cases. So in this lab, our goal is to figure out which case is exhibited here. So case number 1 is this. We can have kV equal to mg. We can say that the drag force is proportional to the velocity. That was model number 1, if you remember, from the text. And from the lab, both, from your textbook and your lab. Model 2 is that kV squared equals mg. Okay, these are the 2 models that we talked about, where k, remember, k is some lumped parameter. I use the phrase lumped because there's a bunch of different parameters that are all integrated into the variable k. So in the lab, we want to figure out which of these 2 models actually holds true. So we can do this several different ways. First, we can recognize here that mg is really the same thing as the number of filters. And let's think about that for a second logically. Let's just use logic here. If I have double the filters, I'm only doubling the mass, right? I'm not changing gravity here, it's still 9.8. If I have triple the filters, I'm tripling the mass. If I have 4 times the filters, I'm quadrupling the mass, etc. So as we increase the number of coffee filters, what happens is that this value goes up. Everybody sees that? The weight of the actual dropped mass, the coffee filters, increases. It's double, it's triple, it's quadruple, it's quintuple every time you add an additional filter. So if this quantity, either model, if this quantity goes up, what has to also happen as a result for this to still hold true? Think logically, what has to still happen?
Velocity has to go up.
Good, the velocity K is a parameter. Remember, K is a lumped parameter based on the air resistance, the cross-section area, not air resistance, the cross-section area, the drag coefficient C, and the density of the air, or the fluid is traveling through, air in this case. So K is not going to change, so V must change for these problems, which is why we have to drop it from a higher height. Again, let's use logic. 2 coffee filters are dropped, meaning it's going to fall faster, because if this number is greater, then this number must be greater. Or in this case, if mg is greater, then v in the v squared must be greater. So we notice that the distance in all of these cases went up, because it's traveling at a faster rate, because it's more massive. So if we drop something that's really light, it's going to reach terminal velocity. Okay, that's fine, but it's going to reach a terminal velocity that is far less than a heavier object would reach. So again, I drop a feather or a piece of paper, that starts to do this right away, right? It's pretty much reached terminal velocity right off the bat. It's actually slower than terminal velocity in a sense, right? It's kind of actually doing one of these, which is a weird situation when you think about it. It's not technically moving down at a constant rate. But the coffee filter versus the marker right here. I mean, if you drop them, right here, actually perfect. If we drop these, it's very obvious in this case that they move at different rates. I mean, it's clear as day. You can see it right off the bat. Now, you might say, oh, it's because there's less cross-sectional area here. And that is part of it, for sure. This is more streamlined than the coffee filter. So that is 100% part of it. But the mass of this marker is probably like 10 or 20 times the mass of the coffee filter. So it's obvious, again, that although they both reach terminal velocity eventually, this probably doesn't reach it in the smaller fall. But even though it doesn't, it's still accelerating downward. The velocity of this is going to be greater for sure than the terminal velocity of the coffee filter. So the distance traveled has to be greater in these cases, because how are distance and velocity related? They're directly related. And that assumption is that there's no acceleration. Think back to our formulas from earlier in the year. This is where we have to kind of tie everything together. Earlier in the year, we looked at this formula right here. We said x equals x0 plus v0t plus 1/2 at squared. Well, if we reach terminal velocity, this drops off right here. There's no more acceleration. There's absolutely no more acceleration. The premise here is that all of these coffee filters ended where? At the ground, or at the bottom. So x final in all these cases is the same, or they're all 0 in this case. So it turns out what we get is this. We get negative x0 equals v0t. And it looks at first like, oh, well, there's a negative now. Oh, my gosh. Ignore the negative. Don't let that bother you. The recognition here is this. So if x0 is greater, then v0 is greater. Again, if x0 is greater, then v0 is greater. Remember, v0 is a negative quantity, because which way is the coffee filter moving? It's moving down, right? And what is v0? Remember, v0 in this problem is not 0. Sure, it's a free fall, so you want to think v0 is 0, right? That's the first thing you think. But when does our problem start? Not when you drop it, I'll give you a hint. When does it start, Em?
It reaches terminal velocity.
Good. The whole key of this problem, and the author is making here an assumption that it reaches terminal velocity almost instantaneously. So the moment it reaches terminal velocity, we begin our problem. And we've talked about this a couple times now. When does the problem begin and when does it end? One of the most important things in physics for all the free response type problems you're going to see, from parts A to B to C to D, right? Where does it begin and where does it end? So our problem begins when it reaches terminal velocity. That terminal velocity in this problem is v0. This is terminal velocity right here. So again, as we recognize from this equation at the bottom, kv equals mg, or kv squared equals mg, this tells us already that as we have more coffee filters, we're going to get a higher value for v. Well, if we have a higher value for v, ready? A higher value for v, but they're going to reach the ground in the same amount of time, then x0 has to also be a higher value, which is why these numbers kept increasing each time. The question that we're going to present now, though, is this. Does our data follow either model A or model B? That's the real question we have to ask ourselves. Does it follow model A or model B better? Now, swipe down a tiny bit on your lab, and you're going to see a graph there. You're going to see a graph there. And on that graph, if I recall, it says to graph the number of filters on the y-axis and the distance on the x-axis. So again, number of filters versus distance. So I'm going to pick the data here that I want to choose. Let me see. And I'm just using one that generally increases, to be honest. So, Chip, for your outlier of data there, you might want to reconsider just looking at that one more time. Just because it might throw all your data off. And I'm not saying you should manipulate your data, but maybe reconsider just looking at it again during some free time. So I'm going to start with this one right here. Okay? I'm going to start with this column right here. So I'm plotting number of coffee filters, which is really like I'm plotting what? The number of coffee filters is analogous to the mass, which is analogous to the number of coffee filters is like mass. The more mass you have, the more. Let me see. Just for a second. Kind of like velocity, we're going to get to that in a moment. But if we have more mass, the object therefore has more energy, velocity is all right. What's the word we're looking for? FG. The weight of the object is greater. Sorry. The weight of the object is greater. So the more mass we have, the more weight we have. So really, when we talk about increasing the number of coffee filters on the y-axis, and I look at the graph of this, on the y-axis, the number of coffee filters is, again, really indicative of the weight or of the mass. So we've got 1, 2, 3, 4, and 5. Okay, again, where n is the number of coffee filters. You guys are going to be doing this on a much neater graph with grid lines, so it'll look nicer for you also. You'll be able to look at your line or curve that best fit. Next. Along the x-axis, our goal is to plot the distance dropped from. So we're going to have a jump in the graph right away. We don't want to just ignore that. So for the sake of this, we're going to go up to, like, say, around 150. So I'm going to go by 50s here. Okay, and I'm estimating what it looks like on my graph, but I'm going by about 50 on my axes here. And again, along the x-axis, we're plotting distance d. But what is distance really analogous to based on what's up here circled in blue? Distance, which in this case is x0, is analogous to velocity. So although we're plotting number of coffee filters versus distance, you want to think about as if you're plotting weight versus terminal velocity. That's really what you're plotting here. You're really determining a relationship between the number of coffee filters and distance, but that is inherently the weight and the terminal velocity. And what is our goal? Look, right here in the middle. Pick a model. Choose which model works best. And look at what they are. It's weight on one side and velocity on the other. Weight on one side, velocity squared on the other. Well, we're doing weight versus velocity. That's what we're trying to plot by using number of coffee filters and distance though. So in this problem, if we plot it, let's take a look what we get. One coffee filter is around 70. We said we're starting. So there goes that. 2 coffee filters is 98. 3 coffee filters is 110. 4 coffee filters is 130. And 5 coffee filters is 154. So that's what my data generally looks like right here. That's what I'm getting. And the question is this. We can do this several ways. The question is, which fit is better? If I were to think about, again, this is weight and this is VT. Is a linear fit, a quadratic fit, a cubic fit, an exponential growth fit? Which of those fits is best in this circumstance? And that will allow us to see which of these models works better. Spence? Why quadratic in this case, would you think?
Because from 70 to 98, you can see a steeper curve.
All right, so let's take a look. So this is a delta of 30, right? Approximately? 28 to be exact, I should say. So I'll be exact, sorry. So that's an increase of 28. The next increase is what?
22.
22. The next one is?
19.
And then finally, 25. So our delta is rather inconsistent in this one, right? It's rather inconsistent. Yeah.
It's 12, not
Thank you. 12, not 22. Sorry. It's all right. I did the same thing. So it's 12, not 22. So we have 28, 12, 19, 25. Interesting, right, to look at? What about the next one? We've got 38. It looks like 17, 25, and then 28 for the last group on the far right. The first one was increase of 70, then 20, then 20, then 20. That was actually rather consistent at the end. Who was the first group? Who was this again? And it went up by 20 the last couple. So the premise here is to recognize or to see in this problem whether you have a linear or a non-linear fit. If it's a linear fit, the delta values would all be approximately the same. So the first group, it actually probably is closer to linear for you guys. And that's at a higher region here of number of coffee filters. Do you see what I'm saying? So like this group, it's pretty obvious here. They're going up by 20 for all three of these. The first one, they go up by 70. So that's a bit of an interesting case to look at, right? It jumps by 70. And then after that, they only go up by 20 for every successive coffee filter. So it looks actually in this region like it's linear. But in the beginning, from here to here, we can definitely see a big spike compared to the later jump. So the lab is really trying to push you to recognize in this problem here that you could have certain models based on what you have for a graph. So if my model looked like this, I'm going to give you the two scenarios that we're considering, versus my model looking like this. Those are the two different models. And in model 1, the slope of that line would equal k. Let's think about that logically. If I were to divide by v, take a look at this equation right here. I'll write it out again. Take a look at this equation. We've got kv equals mg. And again, mg is really the weight. And this is really the terminal velocity times k. Well, if I were to divide by v, we would get k equals the weight over terminal velocity. Well, look at what we have here. The y-axis is really weight. The x-axis is really terminal velocity. So this is the change in y over the change in x. And by definition, change in y over change in x is slope. That's what slope is. So in the first model, if our data went up by a consecutive delta value a consistent delta value every single time, now we would say that it would follow a linear fit. And our graph would literally look like this, right here, the green one at the top.
How is the x-axis terminal velocity?
Because what is the x-axis that we plotted? We plotted distance, right? And what did I mention to you? We started off the whole lesson by going back to kinematics. And we said up here that the distance is really x0. That's the starting position. That's how far it's going to travel. If you started at 200 centimeters, you're traveling 200 centimeters. And we know that they took the same amount of time to hit the ground because we made it work that way. So if the distance goes up, then it must be traveling at a higher velocity to cover the higher distance or the longer distance in the same time period. So the distance is directly related to the velocity. So although the x-axis is distance, it's really the terminal velocity. And although the y-axis is the number of coffee filters, that one's a little easier, that's really the mass. And mass is really like my weight. So really, when I plot coffee filters versus distance, is really weight versus terminal velocity. That's what we're really plotting. So by solving for that, I want to get weight, which is this, divided by terminal velocity. So I take weight, I divide by v, I get this k over here. So that's what gives me the k value. But if this didn't work, I would have to use model number 2. And model number 2 solved the same way would look like this. It would be k, whoops, let me go back, sorry. Model number 2 would look like the following. So that was model number 1. Here's model 2. It would be kv squared equals the weight. That's model number 2. And if I were to solve model number 2 to get K, it would become the following. It would be the weight divided by V squared. So, this is interesting. I did not plot anything to do with weight versus V squared. Right? We plotted weight versus V only. So really, if we were to get a curve such as this, right here, that would indicate to us that the fit is not linear. That the fit is not linear if we got a curved pattern like this. And instead the fit would be like quadratic. Spencer was mentioning earlier, quadratic. Well, what we can do is called linearization of this. We can linearize this, and what we can do instead is now plot the number of coffee filters versus D squared, not just D. And take a look. Number of coffee filters, again, what is that analogous to? What is that analogous to in this problem? Number of coffee filters? Weight. And D is analogous to what in this case? Velocity. So this is really the weight divided by velocity squared. Everybody sees this, right? This is the weight, delta y, over the delta x, which is velocity squared. Isn't that what this is right here? The weight over v squared. So if I were to plot this, it would take my parabolic data and it would cause it to become linear. What we'd be doing is we'd be taking data that should be parabolic, and instead of plotting it against x, we're plotting it against x squared, which makes it look linear. So what we're doing here is this. We're changing our independent variable to become the square of what we recorded. So if you look at your data, you all recorded distance, and distance is the independent variable. So you know how there was a third column there? You all asked the other day, what was that third column for, right? It was like, oh, there's a third column. Do I fill it in? We know, leave it blank for now. That third column is to actually calculate d squared for each of these. So go ahead now, if you can, please. Go to the third column. Square the d value you wrote down earlier. Square the d value that you took down. So whatever that is. So 70 squared, 140 squared, 60 squared, 180 squared, 200 squared. And take a look at that as your x coordinates now, instead of just the distance. Use the square of the distance as the x coordinates on the second graph now you're doing this. We have two graphs, right? The first graph you can plot what we plotted earlier, number of coffee filters versus distance. And for your graph, see which curve fits better. Just estimate it, right? But on the second graph, on the next page, please, plot the number of coffee filters versus distance squared. Whichever is a better fit is the model that the coffee filter abides by. Again, whichever is a better fit is the coffee filter, is the model which the coffee filter abides by. So is your first linear function at the top the better fit? Or is n versus d squared the better fit? So I'm going to circle them in yellow. We're looking at the first graph, which is this. You all graphed that already. And now you're plotting n versus d squared. Whichever looks closer to a line is the better fit. And I know, trust me, I get it. That like, why should this look like a line? It's parabolic. But think about what we're doing here. If we were to literally divide by vt squared, now we're getting a constant k value here, which is the slope. Just like this was the slope over here, delta y over delta x. It's just that our delta x is now a squared quantity, indicating that it was really a parabolic fit if this one looks better than this one. But they're both going to look like lines because we just took parabolic data, and by dividing by the square of the independent variable, we've linearized it. We've made it into what we're going to think of as a linear function. We can try this with perfect parabolic data to show you that as well. I'm going to do that in a moment because I know that your data is not perfect right now, meaning it's not going to fall into one of these cases perfectly. None of your data is going to work with one of the cases perfectly, but it's which one works best is what we're trying to figure out here.
So we squared ours and the values look more like a parabolic curve.
Oh, okay.
But I'll square that out. It could be not best.
Well, yeah, you say wait, so you squared your first chip, and then you plotted it like this?
Well, I'm just looking at the values right now.
Gotcha.
Definitely.
When you square them though, if your original data is parabolic, once you've squared this, the graph should look linear actually.
Well, because my graph right now, before I squared it, it looked linear.
Before you squared it, it looked linear. Okay.
Maybe just because of the way I think.
Okay. Again, Spencer's group definitely looked linear. After that first jump from 70 to 140, theirs is just literally like 20 each time. So they had like what looked like here to a big jump, and then what looks like a linear fit the rest of the way. Yeah.
For ours, they both look linear.
Both look linear.
This one will look less, but it's still it's way. I don't think I'd be considered.
Well, what we'd be doing really, right, what we'd really be doing, I'm going to show you in a moment, is using a regression tool to find the R squared value or the correlation coefficient to see which is the better linear fit. So I'll show you how to do that on the computer as you're going through this to make it a little bit easier on you. Now you can obviously estimate it to see which one looks better, which of these follows a linear fit better at the two circled graphs. But let me show you on the calculator how you can do it. So take out your TI-83 please, or TI-84. I'm going to run through how to do this with you so you guys can all see it. I'm going to make up some data for mine, okay? Why is my calculator down?
Why is distance
Squared?
no? Why is distance x axis instead of y? Because if the coffee filters, the number of coffee filters is constant.
The number of coffee filters is the weight, and we're trying to solve for k. So if we think about solving for k, it becomes weight over v squared. So this is my delta y, so that's on the y-axis. This is my delta x on the x-axis. K is your slope. K is your constant of proportionality in the problem. So it's y equals kx. Like remember direct proportionality?
Right.
That's what we're really looking at here.
Right.
How is this possible that my calculator is missing? Give me one sec, guys.
No, I like his pen. That probably doesn't help.
I like that.
He's definitely lost in
Max, you're just jealous that you couldn't pull them off.
The one day I need to use this, really? I'm sorry, guys. I updated my computer yesterday. It took like an hour, and now the calculator program I use is not on the taskbar, and it can't be found. Virtual TI, come on. Okay, I think I found it. I got to install it, of course. That's freaking great. There we go. All right. So here's what we're going to do. Sorry about that. All right, here's what we're gonna do. I'm gonna clear this first. Hold on. So what we're gonna do is we're gonna go through a quick statistics intro. Very quick, very quick. We're gonna choose this first option here under statistics. Everybody choose statistics. We're then gonna hit enter on edit. We're gonna clear out these lists. So to do that, go up to L2 or L1 and just press the clear button. And it'll clear out the whole list. Go up to L, if you have anything in there. If you have nothing in there, don't worry. So go to L1 or L2, hit clear, and then hit enter, it'll clear your entire list. Now, what we want to do is we want to plot our values of X and Y here, and then do a regression test to see. So, for example, I don't know whose data to use. Matt, I'm going to use your data. You said both yours look linear. I'm curious as to why that is. So I kind of want to investigate that. So Matt, for your data, I know the Y value for everybody is 1, 2, 3, 4, 5. That's easy. That's the number of coffee filters. Can you read yours again to me? From low to high. 70.
Yeah, 70, 108, 125, 152.5, and then
Okay. So I take a look at Matt's data, and what I want to do is I want to perform a regression on this to see if it fits a linear model. We can use Desmos and Excel and other things, but I mean, the exam you can't. So we're going to stick with a calculator, what we can do here. And there's definitely more you can do with a computer tool here. So what we want to do though is we want to actually perform this analysis. So we're going to quit out of here. We're going to go back into statistics. So I quit out once I put those lists in. I'm going to go back to statistics. I'm going to go over to calc, and I'm going to look to see that I've got some options here. I've got this thing called linear regression. Do we see number 4 there? And number 4 tries to take my data and plot it as a linear function. So let's start by choosing linear regression. And simply hit enter here. And it's going to give me some values. It's going to say, all right, we've got A equals 0.037. That's interesting. And B equals negative 1.75. Yeah.
wait, is this, do I just present this first? It's like,
This for about 2 minutes. We're going to talk about where you store one thing regression. Remember I was drawing. If you got the calculator, there's a bunch of options to show that the calculator. If we're plotting, you want to see that it's either the first model or it's KV or the second model or it's KV squared and that. So the thing about this last class was this. For the model to follow KV squared, I was giving you guys sample data. And the sample data that I made up was following the wrong model. So let me show you what. Absolutely right. Very good. So I'm going to discuss what that is actually. That's exactly right. So Max, feel free. Why don't you discuss what R is? I was going to discuss what Max is in stats, so he knows what it is. Yeah.
It's like the average distance between the line and the point that we have.
So Max is talking about what he's referring to as like a deviation. The closer R is to 1, the closer these points are to the line. So if I suddenly have 2 data points out here, R goes down. If I have 2 data points up here, R goes even further down. But if I suddenly have all these data points along the line, now my R value is going up a lot. And if the max R can be is 1. When R is 1, what does that mean? It means the data is perfectly linear. It follows the curve or this line perfectly. So we're talking about the correlation coefficient here. And the goal in these problems is to see which has a greater R value. Whether it's this one, now, I don't know why mine doesn't show it. I think it's because it's the old emulator. Does everyone else though have 84 where it shows, does yours show R on it or not? Some do and some don't. Why is that? Yours does not? It's really interesting. We gotta figure out why that is. But you, like, Kara, hold up your calculator. It's 84, right?
Yeah.
And so is yours here, right? Aren't these identical?
R squared is literally almost y.
It's literally the same calculator.
Imagine your
We gotta figure out why that is. I don't know. What is the mode? His mode is on math program. What's your mode? Some class over there. Math program. you should see on your screen right here is an R and an R squared value here for your group. If you use your data, obviously. If you use the same data as I just put in for master, then you're going to see the same as what I don't have, because it's not listed here. What you then want to do is the following. You then want to go back into stat, go back into edit, and you could actually change these to be the squared values to see if that's better. But to see what we're physically doing, so you guys can visualize this, take a look at what you can also do. Press Y equals, go up to plot 1, hit enter on plot 1. Okay, so we went to Y equals, go up to plot 1, hit enter on plot 1. Oops, trying to hit enter, okay. Now, after you've done that, press zoom, and it should be number 9. It's called zoom stat for statistics. See number 9 right there, zoom stat, and choose zoom stat. And what it does is it automatically rescales your X and Y axis so that it'll fit any data that's in list 1 and list 2. So you can see literally the 5 data points from Matt's group. And you know what else you can do is this. You could actually graph that linear function that we got as a result. And I could see those values here. So 0.037. Now my calculator, for the sake of this, I'm just going to type it in. You could actually have the calculator do this for you. So 0.037, and that's X. So that's A, which is the coefficient of X, and then B is minus 1.75. Minus 1, whoops. I gotta go to the end, sorry. Minus 1.75. And then when I hit graph, it's automatically going to keep the setting the way it was. And look, oh, my data's pretty, or Matt's data in your group is pretty linear. It's pretty linear. You figured it out?
Yeah.
I figured out too, we have to go to diagnostics on.
That's awesome, both of you. Thank you. So is that under catalog?
Figure that out.
Catalog? Diagnostic?
Where do you
And turn it on?
On and just hit enter. Yeah.
And then run the same iteration?
Yeah, and it just shows up.
Ah, nice work. Awesome. Okay. So anyone else see that?
What's a stat wizard?
Stats. Right there. So yeah, nice work, guys. You got the R squared value. So the key that I want you to see is that, again, you can graph this line. There's an easier way also to graph this line and automatically have the calculator put the values in right here. There's another way to do it. For me, I don't think it's going to show on my calculator because I'm using an 84 up here, an 83. For the 84s, though, a lot of you had an option that said like store regression equation. You know what I'm talking about right now? So go back and rerun this, but don't hit enter, please. Go back, go to stat, go over to calc, choose number 4. When you get to here, linear regression, right? When you get to this point, I think a lot of yours has more options, right? So go to stat, go over to that, choose number 4, okay. So go down to store regression EQ. Everybody there? Now, press the following commands with me. I want to make sure everybody's there first before I do there.
Do the stat.
Stat, over, and 4. Go down to store regression equation, and here's what I want you to press. Press variables right here. This is vars, variables. Choose variables. Okay, I'm going to do it on mine. It's not correct on mine, but I want to just demonstrate it. Choose variables. Then go over to Y variables. Then hit enter on function. And you want to store it where? In Y1. So you're going to just choose enter on Y1. Now, for me, to do it on my calculator, because it's an old calculator, I have to type in like list 1, comma, list 2, comma, Y1. That's the command prompt for this. I don't know how I remember that from high school. I think it's list 2, comma, and then it should be. This is how I would do it on mine. Saying list 1 is my X, list 2 is my Y, and store this all on Y1. For you guys, you have list 1, you have list 2 already selected, right? And then under store regression equation, you just need Y1 to appear. And then hit enter and calculate. Now, you might think, oh, nothing happened. I'm getting the same result, right? But now go to Y equals. And you'll see the exact equation in Y equals. the calculator takes the A and the B value it determined and uses those as the coefficients in the function and puts them right into y equals. You have a look in your face.
Yeah, that's just crazy.
It's kind of cool, right? So I go up here and I see, there it is. Everything to the exact decimal, or close enough to the, as precise as we can get here for the values. And again, when I graph it, it still looks quite linear. Now, again, your correlation coefficient is important. I want you now to plot it against d squared. So, if I want to plot it against d squared, I don't know if there's a quicker way to do this. Can we just enter? Let me see. I have an idea. Take a look. Let's see if this works. I'm going to go back to stat. I'm going to go to edit so I can edit my lists. Yeah, so let's make L3 our new x-axis, L3. Can we set this equal to L1 squared? Does that work? That's what I'm asking. You know what I mean? Can I put like, I don't think it works that way, right? Let's see if I can do it. Watch. Let's see if I can do L1. I don't know if this is going to work. Squared. I want to take list 1 and square it and put it in there. It does! Bam! See, I've never done this before. That was just an idea. So ready? Watch what you're going to do. So go up to list 3. Hover over the list itself, not the first entry. And simply type in L1, which is second, and then the number 1. L1 is down here. It's kind of hidden. Choose L1 there. And then, I've never done this before. That was a complete guess. So that worked out nicely. And then square it, and we'll get all the squared values for list 1. Just makes life easier than actually doing all the work. So now, how do we change it though? Bear with me, please. Stay with me. We go back to the home screen now. Chris, you behind a step? Are you good? You good? Okay. You're going to answer the question? So we go back to the home screen. What's the difference we have to make here? Chris, go ahead.
Instead of L1 is L3.
Yeah, for the X, instead of L1, X is now L3. So on my screen, because mine is an older calculator, I'm going to choose the same entry mode, but where I put L1, I'm now going to rewrite L3 over L1. Because remember, we're now changing our X to be list 3. So when you guys have yours, it's going to say X, Y, right? Is that what it says, X and Y? X list, Y list. Yours should be L3 for X list. And then still L2 for the Y list. God bless you.
Oh, thank
How do I get L3 on
How do we get L3? You press second and then the number 3.
And then
So mine looks like L3, L2, Y1. Yours should be L3, L2, Y1 in that order. Okay, L3, L2, Y1. And then you're going to hit enter again. And look at this data though. Look at this one. Which is better actually. 0.982. I didn't write down the last ones. Did anyone write down the last
I'm
ones?
pretty sure it was, here, wait, I can.
Can you run the last one against them?
Yeah.
Yeah.
It's 0.989.
Give me the R, just the R values for now. It's the same thing as getting R squared, you know?
994.
For the first one,
Yeah.
it was 0.994. And for this one,
Or I guess
ooh,
991.
0.991. So it turns out that the model that works best for maths application was the linear model here, not the squared model. Again, because this correlation coefficient is greater than this one or closer to 1, it means the data from the first set of analysis that we ran is better or more closely fitting the actual curve, or in this case, the line that we're looking at. Okay, it's called the correlation coefficient. So the concept is this. Let's take a look, and I want you guys to, we're going to go back to the lab for a second. I'm going to go back to Notability here, or whatever this is. And I'm going to make up random data now to prove what I'm doing to you so you can see a little. So if the sample data instead was given like this, if n was again the number of coffee filters or whatever it is, the weight in this case, 1, 2, 3, 4, 5, and that's the y value really, right, or the dependent variable. And then the independent variable in this case we said was d, the distance that it traveled, which was really the velocity. For this to work, I kept using perfect squares. Remember I was like 9, 16, 25, right? Okay. I needed to use perfect square roots, or square roots, not perfect squares. So that's why the data wasn't working. So for example, if instead this was like the square root of 1, the square root of 2, the square root of 3, square root of 4, square root of 5. And if we were to look at this model, and if we were to actually take a look and say to ourselves, okay, if we plot n versus d, this is what the graph is going to look like. It's going to be a square root function. And you should be familiar with this from calculus by now, the square root function, right? It's kind of like the parabolic function, but it's been rotated really and reflected actually both. It's the inverse function of it is what it is. So this is the data I should have given you, and then as a result, in order to linearize this data, we can simply square all of these d values. And if we square them all, the results we get are just 1, 2, 3, 4, and 5. And then what we'll notice is that if we plot n, the number of coffee filters on the y-axis, and we plot d squared, which is really v squared on the x-axis, now the relationship is absolutely linear. Every time this goes up by 1, this goes up by a certain amount. Whether it's 1 or 2 or 3, whatever it is, doesn't matter. But it's a constant increase every time this goes up by 1. So now, if I were to plot this, and this is what we were looking at last class, if I were to plot n versus d squared, this would look like the following. So when your data involves what looks to me or what looks like square roots, even though the number might not be there, it might actually have a value like 1.414, 2, 2.2 something, 1 point something, I don't know, 1.7, whatever square root of 3 is. Those values can be listed for d. Part of what this question is asking you to do is to recognize that it's definitely not a linear fit if this was the value, because this is clearly not going up by the same amount each time. Okay, it's not going up by the same value each time because it's under the square root that we're looking at. So I think this morning you guys had a recitation with Alex, and I asked him to try to begin a AP level free response drag force problem. And he said you guys went over the homework first and did that for a while, and just barely began the AP problem, right? At the end, you just, I think, did the first part only, he said, like part A or something like that. I'd like to continue going over that. I do want to do that when the whole class is here, though, so I'm going to go into 6.5 after this, but I do want to revisit that AP problem. So in the next week or two, if you want to look at it again, I would recommend doing so. There's really only one part right now that you wouldn't be able to answer based on some calculus you haven't learned yet. And it's literally only one part. And I forget which part it was. I think it's part B, I. You know, there's a B, I, and double I. It's part B, letter I. That's the only part that involves a bit of calculus you haven't seen. So you can skip that part.
I honestly don't remember much about it. I was kind of still.
It had to do with giving you the velocity function. You have to find the position function by integration, and you have to use the acceleration function by the derivative. So to get the acceleration, you can easily take a derivative. But you haven't really done a lot with integration yet.
Just started like finding the area.
Yeah, exactly. So then this would be an integration involving exponential functions, which is just a little more tricky than a simple power function like x squared. To integrate x squared is really easy. X cubed over 3, you raise it up 1, divide by the new variable, the new exponent. But when it's an exponential function, it's a little bit different. Have you done stuff with exponential e yet? Yeah, okay. And that's a topic that in calculus, I hate that this happens, but Mr. Linus teaches exponential and logarithms as an entire topic of its own after you've learned integration. He covers those two topics with derivatives and integration at the same time, but not until you've learned integration. So you guys haven't even done any derivatives with exponential or logs, and you haven't done integration at all / with exponential or logs. So that one part of the problem would be tough to do, and there was really part B that involved that.
Yeah, it's our textbook, so that's
It is. It's the order in which the text goes. I know Larson. Yeah, when I taught AP Calc, I did not use Larson, so I'm used to another book. That's why. Where it's all differential, and then it's all integration. It's calculus separately, completely. And you do all the stuff the first time with logs and exponential, and then you do it again when you get to integration. Whereas Larson does it all at the end with logs and exponential. So you'll learn it all, obviously, but for the incorporation here, you'd have to know that topic, and that's going to take a little while to go through, which we, as it is, don't have time to do that already. Chip, what's up?
Just, well, the homework is a little confusing when you're looking at whether or not it was b or b squared, because some of the problems wouldn't say anything.
So the assumption you're going to make now is that low velocity laminar flow is v, and that high velocity turbulent flow would be v squared.
But what if it's high velocity laminar flow?
It's rarely going to happen. Things at high velocity are mainly going to have turbulent flow.
Oh, like, like the ballistic missile, or like a missile like that. So that seems like something that's going to be like.
Yeah, the velocity is high enough though that it would automatically become kV squared. So it's not that both those parameters have to happen, Chip. It's that like if there is turbulence, even if it's not high velocity, it's going to make it kV squared. If it is high velocity, it's going to be kV squared. But if it's low velocity and it's laminar, that's going to be the one or rare time that it'll be just kV. On the AP exam though, they're going to specify in the problem where they're going to give you data. And what you're going to do is exactly what we did here. So if the data given looks like this, it's not linear at all. It's definitely not linear based on this alone. And you can tell because you can actually evaluate all these numbers here. And you'll see that it doesn't go up by a consistent value each time. Now, if you see it looking like this, then it's definitely just kV. But I squared this, so that's why it's V squared in this problem. But you'd have to be given some information to know a little bit more. But the general assumption, and in your text actually, I think they reference it once or twice in the chapter, that it's like there's a certain threshold limit of what's called the Reynolds number. But we don't do fluid mechanics in this course, so it's hard to go into what Reynolds number is. But Reynolds number has to do with turbulent and laminar flow. So they talk about it being, let's see, did they even say it in here? It might have been just in the AP stuff, not in the textbook. Yeah, it's not actually in the chapter here. It always goes right to V squared in the chapter. But it's in the AP like review guide that comes out for physics mechanics. They have both models there still. So although this textbook specifically works with V squared, you have to recognize that at low velocities and laminar flow, it could just be FD equals KV. Okay? Yeah, because you're asking about the homework question, right?
Yes.
Whether to use which one or the other? I would go with V squared because it's based off the chapter.
Some of them did specifically state to use KV squared, but then the others didn't. So
It just didn't say anything. Gotcha. Was it the earlier one that said to use KV squared or something?
Was that the first or second?
It's probably just trying to work you into the problems, and then they drop that topic, or they drop that statement later on to save space. Okay, so I'm going to stop this.